Hello, welcome back to the Geography 701 video series. Most of the time, through the methods that we've seen so far, I've just been explaining things during the Zoom classes and responding to questions you have. This is an exception to that, where basically it's a question that comes up every year, so I normally do this kind of board talk no matter what, as long as spatial regression is a topic for the class. So I'll do this especially, I think the board helps. So this week's topic coming up is spatial regression. So we saw in the last week, we're looking at regression, ordinary least squares, and some on the logistic, and mentioned Poisson regression, although it's not part of the lab. One of the limitations, as we saw come up, is those methods assume spatial independence. That is very much unlikely within any kind of geographical regression. However, there are different varieties of different ways regression can become spatial. Here I'm presenting the three most common approaches. This is not an exhaustive list. There are plenty of other approaches. But as I said, these are the three most common. And they can often be within some kind of workflow. So I'll start with how a standard workflow that incorporates spatial regression might proceed. We may start with the standard OLS regression. I'll pick OLS within the software, at least within ArcGIS. We can actually use other kinds of regression now, logistic and Poisson, but we'll stick with OLS. So we have our OLS. A diagnostic for whether or not we have geography or space affecting the regression results, we can take a spatial autocorrelation test, Moran's eye, not on the data itself, but upon the residuals or the errors in the regression model. So if we have basically clusters of errors, then there is a spatial pattern to where our model is wrong, then that would logically lead to the idea that space is somehow or other hurting or affecting our results. So we can check this and say if it is significant. So if the residuals are not autocorrelated, we can just say we're done. But what if they are? We then, if the residuals are autocorrelated, that may suggest the use of some kind of spatial regression. What kind? We saw a very particular kind that would have been from the coffee paper by Wilson et al., where we just basically directly put location in as one of the independent variables. We had a dummy variable. Is it in Costa Rica or not? Is it in Nicaragua or not? Is it in Guatemala or not? Is it in El Salvador or not? With that approach, you have to leave one out. Honduras is what we left out. Otherwise, the math doesn't work. It'll implode and it's too much of what's called multicollinearity. But that's kind of bringing the country in, or the location in, as a 0-1 variable is probably not going to work in most situations. It worked there because we had the hypothesis that the reason for the errors was the reputation of the countries, and therefore that's something that operates by country, and we could just put the country in. Most of the time, there's going to be something a bit more complex. So I'll illustrate each of the different complexities with the idea of demographic data, political data at a county scale. The first would be, let's take income at a county scale. Is a place's income directly affecting the neighbors' places and the neighbors' incomes? So if the dependent variable has a direct effect on the neighboring dependent variable, that would lead you to pick something called a spatial lag model, or a spatial lag regression. That there is a direct lag from one place to another. So in an income situation, that's saying that the income of Mon County directly affects the income of its neighbors, the income of Preston County. That could be where, okay, if you increase the incomes of one county, of Mon County, they're going to spend at local businesses, and that puts more money in the pockets, not just of Mon County itself, but of neighboring counties. So there is a direct spillover effect of income from Mon County to Preston County, a direct connection between the two dependent variables. This may or may not help people, but I'll put it up. The math of that, what we would see in all three of these is both the inclusion of something called a spatial weights matrix, defining who is my neighbor. And they all put the spatial weights matrix into the regression equation in different places. So the first one, our estimate of y hat, is we still have our coefficients, beta x, and we still have an error term if we are then saying, okay, y instead of y hat. So y is beta x plus error, that's ordinarily squares. We now want to get space in here. If I'm positing a direct connection, I'm saying this W that's my spatial weights matrix. Rho here is a coefficient, and I am using the Greek letters from something called spatial regression models. small green book. Different sources, somewhat irritatingly, use different Greek letters. I'm just telling you where I got mine. In software, you may actually see different values. This WY, what it amounts to is saying it's the neighbor's average of the dependent variable. And it's using the neighbor's average of the dependent variable as an independent variable. This does get to sort of one of the issues from the previous week's readings, where the issue of how do you estimate the regression parameters, the coefficients of beta and now rho, or the standard approach for ordinary least squares is not going to work when y is on both sides. There are approaches, normally we can just let the software figure that out for us, but it is something that exists within that issue. I'll put it that way. I have not encountered personally any problems with how the software does it. The second approach, this is if we, the second approach is if you think, okay, no, it's not something else, or it is something else. It's not that there's a direct connection. So I might, for this, if I think about voting patterns, there isn't necessarily a clear a priori reason for thinking that making Mon County more supportive of one candidate is going to affect how Preston County votes. But even if there doesn't seem like there should be a direct connection, the residuals suggest that there is something going on. That falls under what's called the spatial error model. It instead says, okay, we still have the beta x, our coefficients, but now instead of bringing the dependent variable over, what is happening here is we're splitting the error term into two parts. One of them is saying the spatially dependent parts of the error term, lambda w squiggle, and then the other regular error term that should not have any autocorrelation. So breaking apart that error term, this can say, well, there's something going on that is causing the errors to be related to each other. There's some process. We don't necessarily know what it is. Or we might have a suspicion, but we don't have the right data to actually measure it. And we have that kind of proxied by this lambda coefficient to see how strong is that additional unaccounted for process. And in that political situation, it might be, we don't have a good definition of who's watching what networks in the media markets. But if a particular candidate is spending heavily for the media in Morgantown, Preston County is in the same media market, then, okay, we can't account for where each candidate is spending all their different money. But because of how media markets work, and there's overlap, it's bigger than one county for a market, there is some kind of connection, some kind of relationship, but it's not well measured within our data. We could go with the spatial error model. The third approach in these two, what we're doing is we're adding something in. We are still assuming that the relationship between our independent variables x and our dependent variable y, still assuming those relationships are constant throughout. That may not be the case. The relationship itself could vary. It could be, to stay with the political example, it could be that in one part of the country or one part of the state, a higher income leads people to support one party, but somewhere else in the country or somewhere else in the state, having a higher income leads them to support the other party. The relationship itself is not constant across space. In that case, we then say, okay, the spatial weights matrix affects the relationship here with the independent variables. This is geographically weighted regression. There's been a lot of work on that recently. Recently being in the past 15 to 20 years. The technique itself hasn't even been around much more than 20 years. Mainly because to actually accomplish it, you need some pretty high power computers to make it work. But that's where the independent and dependent variable relationships are not constant. As I said, there are other approaches to making regression spatial. They are less common. There are also, in many cases, they're newer, so you're not going to see them quite as much yet. But don't be surprised if you see other approaches out there as you do your own research. Our work in class will focus on these three. So, if there are any questions, please remember you can send an email, you can speak up in the Zoom class, and for that matter, I did at one point provide a text number that you could reach me. So, if you have any questions, please ask. Thank you for watching, and again, it might be a little bit before the next one, but I will see you at the next video.